yes, with the emphasis on attempting to understand gold systems, learning every day. And this presentation will probably reveal that to no end. Okay, so I did elaborate a little bit more on the title. Not only monzonites, we're also thinking about some of the other subalkali intrusions that we have at Carosue District. I was really hoping that Wally would be here as well. You'll see a lot of the work that I'll be discussing is really on the back of Wally Witt's work, which we've been very fortunate to have had the opportunity to collaborate with. Okay, so what I hope to walk you through today is firstly to introduce you to the Carosue District and some of the understanding about the gold mineralization. I should have put my glasses on, I think. In fact, I will do that. There's nothing to do with that beer. There we are, much better. And first to look at the district scale understanding of the distribution of the deposits in the basin, and then look at some of the major deposits. So now what we think is controlling the distribution of the mineralization and something about the genesis, and then where where Wally's work has really made a significant difference and really opened our eyes to not only understanding the Carosue Basin, perhaps some other alkali in intrusion-related systems has taken us as well, and then go so forth. So just a bit of a history on how we've arrived at some of the thinking in the Carosue Basin and the deposits, and really the big influences, I guess, I've been fortunate enough to work with, and the team that I've worked with as well. So a lot of it was built on the foundation of Sons of Gwalia when they were operating, and of course that's where Wally and Dave Hammond first published some of the learnings about the geology there and the alteration systems. And we had Wally return after quite a break to do some really detailed quality work. In addition to that, on the ground, in amongst the troops on site within the exploration and the production teams, we worked very closely with a couple of colleagues at Model Earth to really put together what I think is a fairly robust structural understanding and integration of the stratigraphic controls on that structural architecture. And similarly, we've had work with CSIRO in trying to not only understand the detail of what's happening at that small scale, but then try to collect a comprehensive alteration data set that gives us the sense or a much better appreciation of what's happening at that metre to 100 metre scale within the system. And in the hope that ultimately we can apply this back into our exploration search space in a much more effective manner so that we can detect near misses and identify new opportunities. You know, it's not getting any cheaper to drill these deep holes. So let's give ourselves every bit of the opportunity to recognise when there is one. And a few other areas of work that we've tried. You know, I'm a spectral geologist from way back as well. So we've thrown that at it, but we're talking about much higher metamorphic conditions than what standard shortwave infrared will typically provide us. So moved on from that. Lithogeochem works to a degree, but ultimately, actually, the big learning for us in the Carosue Basin is just putting the effort back into getting quality logging and working on building teams' understanding and alignment on what we are trying to log and what the implications are for that. So that's made quite a significant difference. And I think, yeah, we've thrown away the need for a lot of lithogeochem and spectral and some of these other more time-consuming methods in recognition that it's really not adding much more to what we could get out of the logging, which was a great outcome. And we've also done a fairly comprehensive 3D seismic survey that's a whole talk in its own right. So I'm not going to go too much into that in itself. But, you know, we've had a few goes at testing a few targets, but I have to say that we haven't had any direct success yet. But, you know, the opportunity is still there, and the appetite is there. So where are we? Already I get the sense that I'm drifting off track with time. Kalgoorlie, down in this area where I spend a fair bit of time these days with Northern Star, across the Meningina batholith complex into the small localized basin of the Carosue Basin, approximately 2675 age, dominantly intermediate basin, and then the Gal Valley granite to the east of the basin here. Sorry, we'll go back. So the other significant deposits in the area, Rebecca Project and Lake Roe, both now in Ramelius's hands. Oh, and so yeah, I'll also point out the big structures, the Keith Kilkenny, which trucks on all the way up to Leonora and right up into the Yandal. That's very evident in all the deep seismic, as is also the Celia Fault, which compartmentalizes the Laverton district, and again is another significant moho tapping structure. So yes, moving into one of the older maps, and I sort of purposely included this because it reveals perhaps the learning and the journey that we've gone on in doing the work in the Carosue Basin. So the Carosue Basin lies between a mafic, ultramafic sequence of the Meningina greenstone to the west, and then to the east the Murrin domain, which also has the dominantly intermediate to basaltic andesite complex of the Edgadina district, where the porphyry deposit and the Walbrook operations are currently in operation with Northern Star. And it's always been thought that and on many maps, the Keith Kilkenny fault runs down the centre of the Carosue Basin, but when we do the detailed work in the deposits, we've had to really challenge that notion, and I think there's an argument that perhaps the Keith Kilkenny in fact represents largely the early unconformity of the Carosue between the Meningina and the Murrin. And then during the inversion, where we see the most significant juxtaposition of the stratigraphy. So here is the Yilgran Basin, which is a classic epiclastic late stage basin, like the Marugals or the Currawangs, Scotty Creeks, so forth. And that is hinged also on that boundary that runs up the east. We see a lot of strain on the east side as we approach that contact with the Meningina. So we're still trying to really resolve exactly where that might be, the structure that taps to the well below the lower crust. Okay, so zooming in a little bit more on the Carosue Basin, or at least the productive part of the Carosue Basin that we know to date. Karari and Dervish are the two mainstay gold operations. And the smaller operations are formerly mined Kena open pit, Luvaronza open pit, and the Kena APRA projects. So generally the stratigraphy, to keep it simple, is a footwall sequence of turbiditic greywackies that sits. So we drilled one hole that went into the footwall and tapped into to that contact. Just to see what if, and generally it's fairly low strain, but quite localized zones of quite contorted folding and so localized partitioned strain within that package. Into the central basin sequence that is the principal host of the known mineralization, or at least the significant mineralization in the district, and that is characterized in simplicity, and the intercalated lenticular lenses of a relatively well-sorted sandstone, crystal-rich, feldspar-rich sandstone, with otherwise grading variations of a much more fragmental volcaniclastic facies that grades through to varieties that are quite clearly direct volcanic breccias and hyaloclastites. So we're seeing varying degrees of reworking of volcanic detritus to very proximal volcanic stratigraphy as well. And then as you move out to the east, you transition to more epiclastic stratigraphy. Then when I overlay the detailed gravity, and this is just yet another project that convinced me the value of gravity. This has been terrain corrected, so we've removed the effects of waste dumps and depth of cover, and it marries really well. Here's a plug for high size. The tomography, it's almost a 1-for-1, and it really does highlight the area of primary focus. Had we had this data set in the early days overlaying with the soil geochemistry, I think I know where I'd be moving into very quickly for the curiosity of that that high gravity gradient in that center. And the other thing that I will say, I hope you can make it out, is the shear zone that we have in here. That was the position that's been interpreted as the Keith Kilkenny in parts. If you track along the section, along the strike of this structure, you'll find generally parts that can be conformable, very unstrained stratigraphy that then changes to really quite intense high strain shearing. But one thing that is quite unusual about the overall basin architecture is that there isn't a lot of folding. Most of it is east facing, and yep, that's cue to go to this slide. East facing tabular stratigraphy. And it wasn't until that we drilled a very deep hole as part of the seismic work in trying to collect the data sets that would be used for correcting and calibrating the 3D seismic, that we realized that there was a big facing change across the hanging wall structure here, in that most of the stratigraphy in the west side is facing to the east. And then as you go across the hanging wall structure, the facing reverses to the west. And then some good work from an honours student that we had down on the exposures to the south showed, again, folding across into to the eastern part. But primarily a lot of the strain is focused on contacts, and hence why the summary schematic here of the stratigraphy is really quite important. It's the rheology contrast between, if you like, the brown units, which are our fragmental volcaniclastic conglomerates, compared to our cleaner sands, which behave in a much more competent rheologically units that are the favourable host to the mineralisation. And often the shear zones will be developed at that contact. And hopefully with a little bit more detail in the deposits, we'll see that. And there's a summary schematic cross-section of what we're talking about. So within the mine sequence, this is the position of the Carosue and Dervish deposits, footwall sediments, and the reversal and this fold architecture. So the deposits, Carosue and Dervish, are sitting on a fairly significant faulted out fold limb. Pretty critical. As soon as you realise that ticks, one of the critical targeting criteria that we would use if we were anywhere else looking for orogenic gold systems. And then just to take a look at the some of the challenges that the early explorers had. The surface geochem wasn't particularly straightforward. So we're looking at surface gold, either from calcrete or auger samples. fairly subdued anomalies. So the white outlines are the known deposit footprints. And the anomalism is you can see there's some artifacts that are coming from the Paleochannel. There's a really high frequency mag lag interference here that pretty much runs across. But what is still coming through, despite the artifacts of the near surface noise, is the strong magnetic response that we see up in this stratigraphy that, if I go back, coincides. Oh no, that will come up a little later. What else? Yeah, and then at this point here, across this contact, is what we've termed, or has been termed for a long time, the Eastern Intrusive Complex. And this is really again, yet another gradient between the low gravity gradient on the west to the higher gravity in the east. The zone of a voluminous monzonite and syenite and porphyritic monzonite phases that are distributed around that fold hinge. So they look like they are intrusions into the key structure. But at the same token, when we go out into the field, out to the west, and in the mapping, you can find the same units as subvolcanic sills that are very much part of the stratigraphy. And there's a story there in the litho geochem that's coming up as well. Yeah, and this Eastern Intrusive Complex is characterized by anomalous copper, bismuth, moly, gold, and tellurium and zinc as well. And so, after doing the work on the deposits and then trying to apply that back out in our search space to find more discoveries, recognizing the structural architecture features that we could see in the deposits, in the gravity and the magnetics, led to the discovery of Apra, and so Apra is the blob here, and the Kena deposit sitting on the margin of the Apra monzonite as well. So we're thinking that we've got things worked out pretty well, and we're on top of our geology. But it wasn't really until we had a student resign from the company and left his master's project that was the opportunity to welcome Wally into the foray. And yeah, that's certainly prompted some very different thinking in as far as mechanisms of the mineralization in the Carosue Basin and potentially elsewhere within the Eastern Goldfields. So just to quickly go over the details of the stratigraphy we're talking about, examples here of our volcaniclastic conglomerates that are generally more prone to taking up a lot of the strain and becoming localized shear zones. So it varies between crystal rich volcaniclastic sandstones of hornblende biotite and feldspars, both plage and alkali feldspars, through to examples here of hyaloclastites in amongst the cleaner quartz sand matrix. And then we see that grade into bimodal crystal rich volcaniclastic varieties as well. So it's a real mixed bag. Hugh Smithies came out as part of the sort of first look around into revisiting the Canalpi, as GSWA have long forgotten about the Canalpi, and they're now making a concerted effort to return and do a bit more work. This was good enough to get Hugh Smithies excited about the cernicatoid and mantle, fertilized mantle type of signature that it appeared to have, even before we even managed to get a geochem plot up. Then we've got the Eastern Intrusive Complex. So it's that material that I just discussed, the GF unit, as it got locally coined within the production teams. That's been intruded by a couple of different phases. So your regular garden variety monzonites, with lots of evidence of fairly volatile, nice perthitic textures and fairly wet in the sense that they have the biotite hornblende content as well. And a couple of other different phases, trachytic examples of porphyritic monzonites, and a lot of these will also have fairly primitive mafic xenoliths included within them as well, and they're part of the story back to the fragmental volcanoclastic sequences as well. So then add to all of that the more interesting phases of sorry, that middle photo is pretty terrible for focus. The syenite varieties as well, and then the spessartite lamprifier variety. And we see some you know, really high alkaline content within these lamprifiers, and then there's a separate phase of kersentite, which we see, and hopefully I can show in Welling Dervish plays a key role in compartmentalizing some of the mineralization. So to just take a quick snapshot of some of the lithogeochem that we have done, just to see if we can map out some logical transitions between some of these units, and in particular the intrusive phases. So this has been labeled and characterized on a geochemical basis rather than what's been logged. And what it turns out is that most of the volcanoclastic sandstones through to the conglomerates overlap perfectly with the intrusive phases, and that we see a nice mixing trend depending on the varying degrees and component contributed from the end members of the lamprifieric material, which is like those primitive class in the conglomerates, through to the better sorted and more fractionated light rare earth enriched, like the yellow units here, that are more distinct with the sandstones and the monzonites. So to break it down, is we're seeing a real mixture between two end members of more fractionated sources through to more primitive, and it looks like we've got combinations of everything in each other when you isolate out the composition of class and to the monzonite, or to the intrusions as well, which is important when we get to Wally's work. So what does mineralization look like? Well, a bit of an enhanced face photo. You're often greeted with a fairly contrasting, very red alteration broadly, but more importantly, it's when you start to see that really strong red alteration shifting into the oranges and greys that things start to get interesting. So loads are typically, you know, can be half a metre to tens of metres across a couple of faces, and nice broad stopes, which, you know, has been the success and the build of the Carosue and Dervish systems. So there's gold, but not all, there's pyrite, but not all pyrite is created equally. And there's certain phases that have gold-bearing pyrite. Visible gold is actually quite rare, and quartz veins are a complete red herring. In fact, they dilute the ore. There's examples of early stage quartz veins that get overprinted by the key gold stages of alteration, and then later gold quartz veins as well. That really don't contribute at all. So a little bit different to a lot of orogenic gold systems is that on the whole, it's a relatively quartz poor system. So just so we, because we'll go into some of the distribution of these alteration zones, so I'll walk you through the general paragenesis that, as we currently understand it, in the two main deposits. And that is an early stage of potassic alteration, a darkening of the rock with the biotite addition, and plagioclase is still stable, and quartz, and there's a little bit of calcite, and importantly the magnetite. So that goes back to that regional mag image where we saw that much stronger enhancement of the magnetic response. that we believe is related to really this broad scale, big footprint of the early potassic alteration. And with that, there's a little bit of chalcopyrite kicking around, and importantly, the reddening of the rock with that hematite too. So fairly oxidized. Then that's followed by sodic alteration. That is a big shift across into strong albite. Biotite's still stable. And we get low grades with the disseminated sulfide associated with that phase. But the key stage of alteration is the K-spar dolomite quartz pyrite alteration. So we've got already a bleached rock that's overprinting a blackened foliated biotite-rich rock. And it's this stage of alteration that is primarily driven by wall rock reactions that are enclosing crackle veining of dolomite microcline plus or minus quartz pyrite, and that's the main game. Yes, there's a later stage overprinting actinolite alteration that's generally restricted to those rocks that have already got high biotite and hornblends, and the exact role of that still don't quite understand, and then a chlorite sericite retrograde. So you can see there wasn't really much point in doing much spectral work when you were just mapping the late stage brittle overprint. Or it could be part of the outer waning parts of the system. So, all right. So examples of this this evolution, paragenetic evolution of the alteration system. So the blue here is a good example, all in one hand specimen of the early biotite. So a lot of a localized replacement on what was already bedding. And primary biotite phenocryst, but we could see that newly formed biotite foliation developing, and with that there is the localized calcite plus or minus magnetite and hematite. There are also some detrital magnetite laminae occasionally you see as well, but by and large most of the magnetite does look like it's newly formed. Then the red zone here is the next stage of bleaching, the strong sodic albite biotite alteration, which then gets so that's a key part of the hardening, if you like, of the more favorable units. And then subsequent events, we're seeing that high rheology contrast between these biotite-rich, more prone to the ductile deformation, to forming this crackle veining, and the influx of the albite iron dolomite. You'll see in other images it's referred to as anchorite, but it really doesn't fizz, so it's not the your regular anchorite of the goldfields. Pyrite and quartz rutile, and the smoky quartz in places too. So a couple more examples. If you look carefully, you can see the washout, like someone's got a watercolor paintbrush of red across the top at hand specimen scale of that albite. Hematite biotite is just starting to change shape and gets raggedy on the edges. And look, I have to say that's not unique to Carosue. We see that in a lot of our other deposits up near Thunderbox at Wonder North, and Ramon up in the Yandal as well. It seems to be a key part of the early stage of alteration. So how critical that is in terms of the latter, more critical gold stages. Then we're looking at the albite. Sorry, I must have missed one here. Nope. Okay. Yep. The albite iron dolomite. Sorry, the key gold event. So, yep, I think you can make it out. In fact, it looks better up there. Really changing of the rock color. Here's that background albite hematite alteration being overprinted by that tanning up, if you like, of the sandstones, and importantly the localized lenses and pyrite stringers that look pretty innocuous at first, in as far as it just looks like it's just pyrite, and they tend to pick up foliations and also fill fractures and take their own sort of orientation. But then when we start to look in detail, so here's a little 2 centimeter plug taken from one of the samples, and this is TEMA analysis, so an automated SEM image, and it shows very nicely the early albite. So that's that pale yellowy tan colors in here. The blue is the dolomite, iron dolomite, listed as anchorite here, and the local disseminated sulfide. But the really key one that for the introduction of gold is these very fine biotite, the green, with very dark brown rutile and pyrite stringers in otherwise a selvage or halo of much stronger microcline alteration. That's all that reddening you can see in the image there. And then to take another example, we have what looks like early biotite from the regular logging, and you can see here's the sample here, that front of bleaching that's starting to happen on the other the darker biotite there. So this is what in some places we're high grade as well, the black stringers, the biotite zones, but what it really comes down to is the introduction of these microcline quartz anchorite veins and with the disseminated sulfides. And in detail, no, that one doesn't have it. Yeah, so that's the alteration stages that we're effectively looking at. So here we are. We're looking at the leapfrog model, rock model for Karari. So the yellows are the clean sands, our more favourable units, the competent sandstones. The browns are the volcaniclastic fragmental conglomerates, that are the ones that are more favourable for focusing the strain and forming ductile shear zones. And then the eastern intrusive complex is that fragmental material flooded with monzonites and syenite intrusions. And everything's pretty much coplanar with maybe low angle discordances within otherwise an east dipping stratigraphic package. And out to the east here is where we see that facing reversal. So everything's younging to the east here, and somewhere about this point it reverses. So then just to spin things around so we can look down the dip of the stratigraphy and also the lodes, and spinning around a little bit more, the principal structures. So this footwall fault, the Osman fault, the fault, I didn't mention it before, but we believe is the dextral fault that has offset Karari and Whirling Dervish. Once upon a time, they were together. All the kinematics on those fault planes fit with the about 1 kilometre offset of those two deposits, and everything you see at the northern end of Karari marries up very nicely with what you see in the southern part of Dervish, so it works quite well. And then there's a second order scissor fault, the young fella. But yep, just to step through, we're first overlaying. So one thing about these rocks, they're already really heterogeneous. It's really hard to, especially as a newcomer, trying to log this stuff, is recognizing, well, is that a shear zone, or is that just my regular laminated siltstone, sandstone type of stratigraphy? But taking that away, we found actually if you dutifully collect foliation embedding planes, and that's what I'm sort of showing here in the blues and the greens, you can start to make out areas of angular discordance just with those anastomosing trend lines, form surfaces that you can build out from this oriented measurements that you've collected. So gee, I'm starting to feel like this is a plug for Leapfrog, but it's not. But nonetheless, it did help to get past the difficulty, particularly in the early stages of the higher level mine, where we're trying to get our heads around what's going on and what the main controls are, and trying to come up with a really simple logging framework that's going to work for building resource models. So there's the structural data. We're also looking at the alteration log. Now, it's not great and consistent to every hole, but you see the reds, that's the good stuff. That's where we're seeing that microcline, albite, pyrite, dolomite, versus the purples, which is the black earlier stage biotite. And then when we switch on the gold intercept, so just doing a filter here of better than 2 grams, just to give you a sense of where the loads are, and the blue represents the model load positions. And you sort of have to go back and forth, but no, I don't have it, sorry. But the alteration is hinged around these step over structures that go across the more competent sands, and then particularly down here, a lot of the structures built up on the contacts of these. And so these are fairly simplified larger units of the more ductily deformed volcaniclastic conglomerates, and in detail there are more internally within that. So size makes a difference as far as, is it more prone to be turned into a shear zone, in essence. So there we go. And this was a great little example that when we were sort of building up this framework and doing a lot of relogging, that really demonstrates the features at a nice micro scale. So we've got the build-up of strain with biotite against this clast. So this is just a bit of NQ core. See the blackening on the contact where the biotite and the strain is building up. This would be our yellow units, the sandstones or monzonites as well over in Dervish. And a lot of the hydraulic fracturing and selective wall rock replacement will be focused in those more competent sands, but with high grade also on the contact. So yeah, it makes for a nice little analog. So just to spin the ore body around. So we're now looking from the east back to the deposit to have a look at it as a long section. So here I've got the hanging wall eastern intrusive complex, all of that fragmental volcaniclastic breccia. If we peel that away to expose the eastern intrusive complex of where all those intrusions are located, and then that's all the grade above 2 grams. It's a little bit hard to see the high grade chute controls. So that's the Osmond fault, the one that's offset the 2 ore bodies. That trace is the intersection of that second order fault, the Youngfellow fault, and you can see it's split the loads. But then when we peel it back to the high grade, so this is 8 grams or better. This coincides with the intersection of the shear zones and the bedding planes primarily. So that anastomosing network gives a fairly consistent steep northerly plunge within the tabular units. So that makes for nice long hole stoping. Now switching over to Whirling Dervish, we're looking down on the Osmond fault. The yellow again is our sandstones, the footwall sediments, the more competent unit, and you can go through that, and there's that contact, and there's absolutely no deformation. But then you get internally within it, that's where a lot of the deformation is. And as sort of a support group within Northern Star, we really try to emphasize the importance of understanding what's happening up to a couple of 100 meters away from the ore bodies, because it can be those shape changes that are happening structurally that can drive a lot of the response in the more competent units, particularly where there's that heterogeneity. So yeah, bang on about that plenty. So here's the overlay of that magnetic data, just a different filter. And you can really see that strong magnetic response, even though, yes, we've got a lot of interference with that near surface mag lag, but that really strong enhancement of the magnetic response. And you can see that in the MagSUS downhole as well, as you get nice rabbit ears, if you like, of increased magnetic response where the biotite is, transitioning to where you're getting that later stage overprint. So it works quite well. So again, we're looking at the lithologies here. The difference being we have a lot more lamprifier dikes that are cutting through. These are those Kersentite units, the footwall sediments, and a bit more monzonite actually within our central mine sequence. And here's that big package of the fragmental volcaniclastics, our eastern intrusive complex, and lamprifiers are the purple here, and monzonites. So that's the architecture we're looking at. And then we put in the structural readings of bedding and foliations, and you can see things are meandering around, and where it can be hard to get, as I say, the geos to pick regularly where the structures are. But just on that, looking at that data, you can start to pull things together, and it starts to make a bit more sense. Here's the gold overlay as well. So here's a classic example. Look, I did probably a bad slice here. And conveniently there's no drill hole, but this lode here does pretty much peter out to not match at all across the lamprifier. So the lamprifiers we see acting as somewhat compartmentalizing a lot of the loads. So a bit shorter strike continuity than what we see down at Carosue, where these lamprifiers are less common, and you can really start to see a slightly different response. The red again is the alteration, the key alteration of that microcline dolomite pyrite stage, and the rest is predominantly the biotite, the earlier biotite stage. Not the best example. Here's the lodes, and you can see the that architecture of shear zones following contacts and then cutting down through the stratigraphy. So generally, the kinematics that we see for most of the lodes, particularly the high grade, is a sinistral wrench system. But given the heterogeneity of these rocks, they are pretty difficult to really map out in detail. So just having a look for the long section, we're going to look back down to the west, Osmond Fault. Taking away the stratigraphy, there's the gold distribution. I think that's everything above 1 gram, just showing you where the data density is, so we know we're not skewing things. And then the long section. But the thing is with where, if you like, we're more at the horsetail of the whole shear system before we've offsetted it with the Osmond Fault. So when you come to look at the high grades, it's really difficult to see some particularly consistent high grade controls, because I think we're seeing that breakdown of the loads. And the Welling Dervish is certainly not the same order of scale as Carosue. So yes, I alluded to the fact that a student stepped out, and so Wally happily picked up the work that he was going to do, and it was really quite mind-opening work. So he did some analyses on the biotite and rutile, not only in the mineralized lodes, but also the intrusions as well. And it was recognized quite early is that a lot of these intrusions were or have a lot of re-equilibration textures unrelated to mineralization, that from the biotite rutile work showed that they were re-equilibrating in their own hydrothermal alteration at very high temperatures and very oxidized conditions as well. And then when you start to look in detail, look at the rutile and the biotite in those biotite rutile pyrite stringers, the stuff that usually contains the coarser gold included in the sulfides in the pyrite, and that has a really distinctively high iron, vanadium, and tungsten, all classic indicators of really oxidized fluid conditions. And again, the zircon in the rutile, the zircon in soluble zircon, showing again very high temperatures, which was somewhat unexpected. in as far as what we're typically used to in orogenic gold systems. And then the sulfides too have a high tellurium and bismuth signature about them as well. Again, elements that we often attribute to more magmatophile oxidized conditions, and the sulfur isotopes are way down there in the negative space, where we know that sulfate is present in the hydrothermal fluid, and indicating just how oxidized things are. So yeah, with John Walsh and Adam Barth doing quite systematic sampling across the whole Carrari and Dervish systems to try to map out what the zonations on that next scale up. Similarly, we got similar indicators of fairly persistent oxidized conditions, and they suggest that we're talking about fairly alkaline conditions too, which we're not usually seeing in most of our orogenic gold systems. Oh yes, and then there was the bringing in of APRA. So the thing about APRA is that we were looking for an orogenic gold system with the usual features of the standard transition from albite dominated alteration with a low grade gold component to the pyrite, the biotite rutile pyrite stringers. A good example here, cross-cutting early quartz veins in the APRA monzonite. And but what we did find is that there was a lot more disseminated copper moly mineralization that was really quite clearly part of the emplacement of the monzonite itself. So here's an example of an anhydrite vein, again with the same many components that we see in our gold-related phase, but here with really elevated moly, and typically has quite high chalcopyrite as well. So is this the smoking gun sort of scenario? And this is what Wally is perhaps alluding to, is that yes, and this is the quandary that I guess this work has done, that we're seeing stratigraphy that's being intruded by intrusions that are exsolving hydrothermal fluids, that are altering it at conditions that are almost identical to the hydrothermal fluids that we can see cutting through these units, and clearly are very structurally controlled, that are identical. So it makes for a very dynamic system of depositing, intruding sills, deformation, upturning, and then the overprint by fluids that are almost identical to what was being generated out of the intrusions, which is, I mean, but the only analog I can think of is lower temperature version, is something like a Kanowna Belle, where we see similar, very contracted period of deposition and intrusion from similar phases of intrusion. So yeah, it's made us step back from where we thought this is a fairly straightforward orogenic gold system to perhaps something where there might be points to a more of an intrusion interlink between the mineralization. And one thought is, well, what would one of these systems look like at a higher level, crustal level, and at lower temperatures? And what would the alteration systems look like? And is there a link? So yeah, I think I'll leave it there. So yep, and there's some references.